Ladies and gentlemen, I would like to welcome you to our first edition of this Rare Earth Roundtable series. My name is Roland Gauss. I work for EIT Raw Materials, which is a large European knowledge and innovation community dedicated to critical raw materials. And this webinar is part of a European project, an EU-funded project, an innovation project funded by the European Commission called Magellan. And you will learn more about this project in the course of this webinar. So I'm really excited to be here with also outstanding colleagues. The objective of this roundtable is really to gather this European rare earth community to share knowledge and information also about latest sector developments, but also to open up this community and invite those people that are not yet so familiar with the phenomenon of rare earths and all the fascinating opportunities that come with it. So we kick off this roundtable series with a number of highly distinguished speakers in the field to reflect on the state of the union of rare earth industry and research in Europe, and how also this is embedded in this kind of changing global political landscape. So we have here Imants Dirba, who's a postdoctoral researcher at TU Darmstadt. We have Fabio Scafi di Muta, a material specialist at CRF and Stellantis Group. We have Alex Barsa, who's vice president permanent magnet at Vakuumschmelze. And we have Benoit Richepé, who's a project director, rare earths and magnet recycling at Orano. So very grateful that you are with me here. I hope also Milan Grohol, a policy officer at the European Commission, will join us later. He has had some technical issues so far to join. And I have my colleagues here with me that support this webinar, Vanessa, Patrick, and Alexandro. So let's kick off with this webinar. We have a very exciting agenda. Each speaker, each participant, each panelist will have 10 minutes to give a short intervention. And each intervention will then have 5 minutes to follow with questions, Q&A. If you have questions, please put them into the dedicated Q&A window, not the chat box, but the Q&A window, so that people can really, we have some exchange, we can raise questions linked to the specific presentations. And at the end of the event, we should also have some time remaining for follow-up questions dedicated to the entire presentations and to the agenda. So with this, I would like to hand over to Imants. Imants is a postdoctoral researcher at TU Darmstadt. But Imants, before you go ahead, tell us where do you see key trends in neodymium iron boron, and what kind of research do you follow at TU Darmstadt?
Yes, at the TU Darmstadt, we are working on rare earths, neodymium iron boron magnets, also rare earths lean, such as samarium-based 112 magnets, also what I will mention later, free rare earths. So we're actually looking at all kinds of different aspects of rare earths and also rare earths free permanent magnets, including recycling, grain boundary diffusion, also corrosion properties, secondary properties. And we are trying to look deeply into material science. We are material scientists, not motor designers. So we investigate microstructure correlated with magnetic properties, look at intrinsic, extrinsic properties. So without getting too complicated, I think I will stop here.
Already sounds fascinating. So please go ahead and share with your insights.
Thank you very much, Roland. And so as mentioned, I will very briefly in 10 minutes try to go through the recent trends in what we would call neodymium iron boron age. As you know, there was Bronze Age and so on. And actually, if we look at the green energy transition, we are sort of entering neodymium iron boron age, or have entered it already, because it's crucial material for electric vehicles and wind turbines at the moment. So the first trend I would like to discuss briefly is operating temperature versus heavy rare earth content. The motor designers know the problem very well. Neodymium iron boron is excellent permanent magnet material at room temperature. However, the magnetic properties deteriorate steeply when the operating temperatures increase, and the motors operate at, let's say, 150 or even 180 degrees, and that becomes really challenging. It's actually impossible for pure ternary neodymium iron boron. And for that reason, historically, the so-called heavy rare earth elements have been added to the magnets, such as dysprosium or terbium. The problem is, as I guess many of you in the audience know, the criticality of especially the heavy rare earth elements, the geopolitical concerns, also, of course, economical aspects of that. So we would like to reduce the amount of heavy rare earth elements to the minimum. So one possible trend would be to lower the motor operating temperature. That is a task for motor designers, not for us material scientists. For us material scientists, the task is to try to design a magnet microstructure where we would have the best properties at 150 degrees, let's say, with using the smallest heavy rare earth amount. And historically, two interesting trends have been proposed, and we are actively investigating them, not only us, but other players globally at the moment. One is applying heavy rare earth source on the surface of the magnet. So this blue block you can see there is a typical sintered neodymium iron boron magnet, and we put heavy rare earth, dysprosium or terbium source on the surface, and then do heat treatment, and it diffuses in the magnet, as you can see by this diffusion gradient here. The second method that actually we hold a patent at the TU Darmstadt are investigating actively together with Fraunhofer IWKS is a so-called two-powder method, where we use a 1,2,14,1 powder, and which is sort of ternary, and the yellow one, which is slightly smaller in particle size, that contains heavy rare earths. And we mix them both together and then do sintering. But the result is essentially the same. We have diffusion of the heavy rare earths only at the grain boundaries. So for those who are not material scientists, it maybe just looks like a fancy exercise, but the advantage is that we can significantly save the heavy rare earths, as I will show later in the slides, by this method. So as I would say, these are the two main trends at the moment, how to introduce heavy rare earths into a commercial sintered magnet. And what we are looking at the moment is, one is physically, how do we do it? What I showed here, do we apply it on the surface or mix it in? The second question is, what is the best heavy rare earth source? And there are very different ways how to introduce heavy rare earths into the magnet. And this graph just shows the heavy rare earth content and the enhancement in coercivity we would get by that. Now, and you can see that the variation is huge. We are talking about adding 100% of heavy rare earths, which would be, let's say, pure terbium or pure dysprosium to the magnet, and having very small coercivity enhancement. And we are comparing that to adding less than maybe 1% of dysprosium or terbium and having huge coercivity enhancement in the magnet. So as you can see, the deviation is really large. And what we would like to get is, of course, something here in the upper left corner where we get the highest coercivity enhancement with the smallest amount of heavy rare earths. And that's also a topic that has been actively investigated in our labs and also globally at the moment. And for example, our conclusion currently is that by using these, let's say, relatively complex quinary alloys with terbium, praseodymium, copper, aluminum, gallium, and other elements, we can actually achieve the best heavy rare earth introduction efficiency. And you can see it here, the black one. So this is typical MH loop of commercial sintered magnet. On the right side, you see the polarization or magnetization, if it was in kiloamps per meter, and the applied magnetic field on the horizontal axis. And the black one is a standard reference sintered magnet with low or no amount of heavy earths, has coercivity of about 1,000 kiloamps per meter. And then if we
a quick question to you talking about coercivity. For those people that are new to the field, what is coercivity? What does it tell you about the magnet?
Okay, I'm so sorry. I sort of assume that probably everyone knows that. So if you look at a permanent magnet, the reason why it is a permanent magnet, not a temporary magnet, let's say, is that it has remanence and coercivity, which means that if we once magnetize it, so we do all the metallurgy, sinter it, and then we once magnetize it in a high applied field, and then remove the magnetic field back to zero, which is here, we have remanent magnetization, which means that the magnet stores energy in it. It stores electromagnetic energy, and produces a stray field in a space around it once the external magnetic field is removed. Moreover, when we put it in the motor or generator, we will have a negative field or demagnetization field because of the current produced by the coils in the motor or generator. And the coercivity, sort of a disk, is the point here where the magnetization is reduced to 0, which means it's basically the measure of the strength of the magnet for resistance towards demagnetization. So the higher the coercivity, the higher is the negative field, the demagnetizing field you can have in the motor before you start to demagnetize the magnet. Because once you demagnetize it, it's done. It's damaged. You can't use it anymore. It's sort of irreversible at that moment. It can be recovered, but you would need to demagnetize the whole thing new. Okay, so the goal is to design the motor and magnet so that you operate it before you start to demagnetize it. And the problem, what I also mentioned in the slide before, related to the temperature effects and heavy rare earths, is that this demagnetization curve here would shift to the right with the temperature. The higher the temperature, the lower the coercivity will get. And that is exactly the reason why we're trying to put these heavy rare earth elements.
Thanks.
Okay, I hope it's...
That makes total sense. Thanks very much.
Great. So just to continue here, so the black one is a typical sintered magnet with a coercivity at room temperature, let's say around 1000 kiloamps per meter. And then we do this grain boundary diffusion with different heavy rare earth sources, where by heavy rare earth source, I mean here dysprosium hydride, terbium hydride, and then some of these more exotic complex alloys. And you can see that the coercivity increase it is normalized to exactly the same amount of dysprosium or terbium we put in the magnet, is very different for these different sources. And the highest actually is for this terbium, praseodymium, copper, aluminum, gallium, okay? And we can, as you can see, we can almost double the coercivity of the magnet by simply diffusing in very small amount of one of these heavy rare earth sources, okay? So this is the main goal and the main trend of this research direction that I want to emphasize is how to enhance the coercivity to the highest by using the smallest amount of the heavy rare earths. Okay, it's a very interesting research direction with a huge practical potential. And another interesting aspect there is here we looked at different sources of the heavy rare earths, how by using hydrides or alloys or powders, we make the diffusion process in the magnet. What we could also play around is where exactly on the magnet's surface we put this heavy rare earth element, okay? And by doing simple magnetostatic simulations, one can see that the Demag field is the strongest at the corners and edges of the magnet. So it would intuitively make sense to strengthen selectively, strategically, only those areas of the magnet. So typically the entire surface, the entire C planes are hardened with this heavy rare earth diffusion. But maybe that's actually not necessary. We would save a lot of heavy rare earths, and heavy rare earths are critical and expensive, so we would want to save them. If we selectively apply them only on these areas where the local Demag fields are the hardest, so the highest would be, let's say here, the edges, and in this case, the corners. And that's another interesting direction that we are looking at the moment, and we can produce such selectively hardened magnets. And here you can see, for example, the top plane of such a magnet that is afterwards cut, sliced, cut in small pieces, and then we can measure magnetic properties of each individual piece and then produce such a coercivity mapping. You can see here we are looking from the top cross-section of the C plane, and the coercivity enhancement is the highest here where the color is green in the color map and the lowest where it is blue. And you can indeed see that if we actually measure the coercivity of those different areas, if we map the surface of the magnet, the coercivity enhancement is the highest at the corners where we chose to put the heavy rare earth source and do the diffusion. Okay, so this is, in my opinion, another interesting trend and research direction, how to try to achieve the same coercivity enhancement and thermal stability of the magnet by using as little heavy rare earths as possible. Now, another, I think, very important trend, especially it's also the scope of the Magellan project that was mentioned earlier, is recycling, of course. Again, rare earths are related to significant environmental and geopolitical and economical concerns. And in Europe, we have actually complete reliance on external sources at the moment. Therefore, it would make perfect sense if we use the rare earths we already have in Europe imported, and we don't export them afterwards as a scrap, but we reuse them. reuse or recycle. So here I'm just showing a typical flow chart of the experiments we are doing in our labs. So we get end-of-life rotors that we machine them up. Here you can see when we have machined the front plate of the rotor and we press out the magnets that you can see here. They look like this in different shapes and different sizes. And then we try to, in ideal case, of course, reuse them if the magnetic properties are good and they haven't deteriorated yet. If it's not possible, then we would need to go through one of the different recycling routes. So we are investigating different routes: hot pressing, sintering, hydrogen route, magnet to magnet, magnet to alloy. So depending on the condition of the magnet, is it heavily corroded or not, we could either directly reuse it or recycle it using the short loop process, or in the worst case, we would need to go through the long loop. And that is, of course, also all hand in hand with life cycle assessment, because the further we go back in the value chain, the more costly it becomes in terms of the energy input, CO2 footprint, and so on when we do the recycling process. But this is definitely a very important research direction and trend for neodymium-iron for the next decade, I would say. Another topic is the light rare earths, or I even dare here to call them free rare earths, because if you look at the natural abundance and balance of the rare earth elements as they are mined up to date, there is significant surplus of light rare elements because they are simply so much more abundant. So if you would mine 1 unit of neodymium, you would have so much more of cerium lanthanum that at the moment, due to the oversupply, is very, very cheap and abundant. And another advantage is that they're available also in other parts of the world, whereas heavy rare earths are concentrated in very few regions globally. And therefore, the question is, could we take neodymium iron-boron magnet and replace part of neodymium with, let's say, lanthanum and cerium? And ideally, of course, without sacrificing the magnetic properties much. And here I just put MH loops, again, the same as I already explained before when Roland was asking. This is the magnetization, in this case in kilogauss. This is the applied negative magnetic field in kilo Ørsted, typical rectangular MH loop of a sintered neodymium iron-boron magnet. And what you can very nicely see that in principle, by substituting up to 40 weight percent of lanthanum and cerium. So this is then the chemical formula weight percent of the sintered magnet, as you can see. So from the total rare earths, 40% of neodymium has been replaced with cerium and lanthanum. And with that, we can achieve a magnet that has a grade of around N35 to N40, which is actually not that bad. That's, of course, not the top N48 or N50 or N52, but there are for sure a lot of applications where N35 to N40 grade magnet still can be extremely useful. And that
I understand, Imants, I understand not all rare earths are that critical or that difficult to get as neodymium or maybe heavy rare earths.
Exactly. So that's absolutely correct. And in that sense, the wording rare earths is almost a bit misleading, because the light rare earths, if you're looking at lanthanum and cerium, they're actually probably not more rare than, let's say, a cobalt, or many other elements that we would use in our daily life. I mean, actually, at some point in the future, if you look at the electrification of the transport now and so on, maybe copper might become more critical than lanthanum or cerium in the next decade. It could happen.
Now, looking at the time also, because we have also other speakers coming in. Do you see any alternative material to these rare earth permanent magnets as you describe them so far? Do you see other materials on the horizon coming?
Yes, so that's a very good point. I'll really try to go through as quickly as possible. So there are actually a lot of possible alternative materials, and you can see many of them here listed on the horizontal axis. So alnico magnets, iron nitrides, iron nickel, ferrites, and so on. Manganese bismuth, manganese aluminum. Many of those materials are actively studied in our labs and different other laboratories. The problem is it becomes a bit of a witchcraft almost sometimes when this is discussed publicly. So people make really huge claims about possible potential of some of these materials. But it's a bit like with other laws of physics, there's certain limits that cannot be broken. And in the case of permanent magnet, one of the relevant ones is the anisotropy field. The anisotropy field is what determines the highest coercivity that we could potentially achieve. And in reality, the blue one is what we actually get in reality. So it is much, much less than that. But with this, I simply want to put it in perspective that there are a lot of possible alternative materials. Most of them do not qualify for a permanent magnet material, simply because the anisotropy field is way too low. If you look, for example, there have been also a lot of media coverage on iron-nickel meteorites. The anisotropy field and the coercivities achieved are simply way too low to compete with, let alone compete with neodymium boron, but to compete even with ferrites. Okay, so that I think just needs to be kept in mind when we are talking about some of these rare earth-free materials. There are several exceptions where coercivities achieve nearly the anisotropy field, but that is actually very low. So if one uses this empirical hardness parameters, then everything that is under this line is very, very difficult for that material to become a permanent magnet. So that could be easily used as a sort of rule of thumb to judge any of such claims. Yeah, so there's, and just very, very quick case study. There's, for example, Fe16N2, and many of you know that there has been, there's actually a startup working hard on this topic in the US and has gained a lot of funding and also media coverage. And with that, I just want to show, if you look, for example, here, the published data on the coercivities of this material. This is starting from 2000 to 2025. Then it is almost all below 3 kiloersted, 3000 ersted, which means that the coercivities are extremely low if you compare it to neodymium boron. And it's also inversely correlating with saturation magnetization. So once the coercivity increases, magnetization is very low. So this just shows that it's very, very difficult for any of these free clay materials to even become close to neodymium boron. It's really very, very far from reality.
Yeah.
Am I out of time?
Yeah, you're running out of time, but it's such an exciting topic you're touching on. Really trying to push the boundary in material science to get the best alloys and then magnet materials produced out of them. So thank you very much. Really exciting stuff. As I said, we'll have a little bit of a time at the end of the talk, a series of talks. So all of you who have written down questions, please keep them for the end of the interventions. Thanks very much, Imants. And I would like to now move on to Fabio, who's material specialist at Stellantis, who's actually, looking at these developments, research and development, and also, of course, innovation happening here, and then applying these materials to produce motors, right? And to develop and sell the best possible electric vehicles. So we are, of course, very excited to hear about the role of rare earth permanent magnets at Stellantis. So Fabio, please go ahead.
Okay, so can you see my screen?
Yes, we can see it.
Okay, so first of all, hello everybody. I'm Fabio, and as Roland anticipated, I work in CRF Stellantis. Before to enter in the detail of the presentation, I want to spend 2 words about my company. So Stellantis, born in 2021 after the merger between PSA and FCA, and we are covering 14 brands such as Fiat, Jeep, Lancia, Peugeot, Opel, Citroën, Maserati, and we have a global and worldwide organization. In Stellantis, CRF is supporting the development and then transfer of an innovative powertrain, vehicle system, material, processes, and moreover, Stellantis is CRF is representing Stellantis in European and collaborative programs. In Stellantis, I'm part of the material technical expertise department that is divided in 3 different pillars. The first one related to the polymers, in which we are managing all the plastics, elastomers, trims, paints, materials. Then the metals, such as sheets, bulk, electrochemical coatings. And finally, a quite new department that is material for electrification, in which I'm working. In this department, we are managing all the new material that are related to the electrification of the vehicle. So I mean material for battery cells, material for battery pack, material for fuel cell, material for electrical electronics, coolant, and material for magnets and EDM. In this presentation, I'm going to show you why the permanent magnets are of main interest for Stellantis, and which are the activities that we are doing in this frame. So, why permanent magnets are of main interest for Stellantis? This is to understand this, we have to get a look to the Dare Forward 2030 Stellantis plan, for which Stellantis has defined some targets. Most of them are here reported. They are the reduction of the CO2 emission by 2030 of minus 50%, refer to the data in 2021. Then for the 2030, we wanted to sell 100% of battery electric vehicle in Europe. And the last main target is to reach the carbon neutrality by 2038. In order to reach this target, we have not only to sell electric vehicle, but we have also to manage the material that are used to produce battery electric vehicle. And this is because the new technologies that are used for battery electric vehicle are really dependent on raw materials and the supply chain for the production of the systems, refer to the internal combustion engine motor. For what concerns the electric motor, here I reported a scheme of a permanent magnet synchronous motor. And getting a look to the material that are involved in this kind of device, we have mainly some non-critical raw materials, such as the aluminum that is used for the frame or for the cover of the motor. Then there are silicon steels that are used for the stator core and the rotor core, and then some plastics material for insulation. And then we have the critical material that are mainly related to the active part of the electric motor, and they are the copper that is used for the hairpin, and then the light and the heavy rare earths that are used for the permanent magnets. Permanent magnets in a permanent magnet synchronous motor are the component that have the less contribution in terms of mass, because in this kind of device, the total amount of permanent magnets is lower than 2 kilograms. But if we get a look to the contribution permanent magnets in terms of cost and CO2 footprint, they have the bigger impact. I reported here as example a study from ZOO, in which is reported that for a permanent magnet motor of 32 kilowatt, the permanent magnets have a contribution of 34% on the final cost of the device. And as you can see, this is the bigger part of the cost. Moreover, getting a look to the declaration of the European Community, in the future, it is expected to an increment in the usage of critical materials such as dysprosium, neodymium, and praseodymium. And as you can see here, for the 2050, it is expected to have an increment of dysprosium of 6 times. And so it's important also from an end user point of view to manage and to develop alternatives in order to to solve the issues related to the usage of these critical materials. So what we are doing in Stellantis, and specifically in the material for electronics team. So our main activities in this department is to support our commodities and our engineering in the development of the new Stellantis programs. In order to support the commodities, we have to validate technically the alternatives that are offered by our potential supplier. And this is important because Stellantis is going or already did some agreements with some companies in order to securize oxides and critical material for the permanent magnets. And here I reported as example the agreement with NioCorp and with Carester. In order to do that, we are focalizing our attention on especially on neodymium and praseodymium as a lighter rare earth, and dysprosium, terbium, and holmium as heavy rare earth. For all these elements, we are investigating and in more detail the different steps that are used for the production of the manufacturing, starting from the mining, the extraction, then passing to the separation and refining to produce the rare earth oxides, the metal reduction to produce the metal alloys, then the process for the production of the magnets and manufacturing, and finally the production of the final component, so the electric motor. We are also defining rules, and we are collaborating in different programs for what concerns the recycling of the material. And especially in order to do that, we are collaborating in some collaborative projects funded by the Hydro Material or by the European Community. And I reported the main here. As example, we have a Discovery Magellan that have the aim to reduce the amount of rare earth and to recycle the permanent magnets. Then to other projects such as a Passenger, a Magneo, that have the aim to develop a new solution without the critical raw material. And finally, we are involved in another project that is permanent, in which we are creating sustainable rare earth innovation and supply network. So, in conclusion, the electrification and sustainability goals has shifted the target of material characterization, because the electric vehicles, as I told, are more dependent on the raw material referred to the conventional vehicle. Moreover, we are working in order to securize, to define a new business in order to manage the potential issues related to the application of critical raw material in our vehicles. And this also in order to avoid eventual material shortages and to prevent some environmental and socio-political impact. So thank you very much for.
Thank you, Fabio. It's very impressive to see all your activities and you're connecting to the different European initiatives actually, and most kind of latest key, very impressive collaboration I just learned a few days ago is this collaboration with Carester. Very impressive. Now we have time for questions. Vanessa, could you read out some of those questions presented in the Q&A box?
Actually, Alex is going to do it because I had a little issue. So,
okay.
Alex, you there?
Yeah, no, I'm here. So there have been a few questions. Actually, there's been one question for the first speaker. I don't know if you want to answer that first, or should I put it out first, or just
maybe start with the last question. I also just opened the window. which is more related to Stellantis.
Yeah, so one question is what development for the speaker from Stellantis, what development will be specifically made in the Magellan project?
So in Magellan project, we are mainly investigating processes and in order to recycle the permanent magnets, and so to have at the end materials that can have a content of recycled raw material in order to reduce the usage of virgin material. And moreover, we are defining new processes in order to avoid also and improve the technology and the scraps in the production of the permanent magnets.
Okay, so it's really recycling focused.
Yes, one of the main activities is the recycling.
Yeah. Thanks. And maybe a quick follow-up question from my side. I mean, this is really impressive to see the kind of these key steps taken by Stellantis. But I mean, looking at this global competition with, supply chains, as we all know, heavily dominated by Chinese and maybe some Japanese players, would Stellantis really be willing to strategically invest long-term in this supply chain diversification? And kind of, what do you think, what would it take to sustain really long-term such a supplier network outside of China, and ideally maybe even from Europe?
Yes, one of the main activities at the long term that we are doing is exactly to collaborate and in different frames, so the European project and also with internal activities in developing new processes and new alternatives for the recycling of the permanent magnets. And also we are working with potential supplier of raw materials starting from mining, and okay. So outside of China. Yeah.
Okay.
So we are in discussion, and as I show, we are really interested to this kind of activities, and the agreement that we already see are an example of these strategies.
Okay. No, that's very exciting and great to hear that Stellantis is really kind of strategically addressing this topic. Yeah, with this, I would love to first of all thank you, Fabio, and hand over to Alex Barca, who's Vice President at Permanent Magnets at Vakuumschmelze. Now more than 40 years of rare earth metallurgy expertise, magnet making. Alex, so what's next for Vakuumschmelze? Please.
Perfect. Yeah, thanks so much for the introduction, Roland. And I don't have all the 40 years on the back of my shoulders. I look much older, but as we love to say, standing on the shoulders of giants. So yeah, let me share the screen. Okay, I have too many. It should be the presentation.
Yes, we can see it. Excellent.
Okay, perfect. Right. So yeah, first of all, thanks very much for the invitation. And it fits actually perfectly to what my previous speakers talked towards. We had a session by Imans where he showed all the latest and greatest on rare earth production technologies, and also a very good overview by Fabio on how the OEMs are strategically focusing on the rare earth permanent magnets. And since my presentation will be very light on the products, but more on a, let's say, view of where do we come from? You mentioned it, around 40 years of permanent magnet experience. Where do we want to go, and how do we get there? So a couple of provocative questions, and I hope we can have a good discussion at the end of the very short presentation. So without further ado, I'd like to introduce VAK a little bit. I took the liberty and also put in soft magnetic materials, although the focus today is exclusively or mainly on the permanent magnets. But since this is such an important topic for the overall electrification, please allow me to give a total overview of WAG. So the company provides high-end specialized magnetic materials, so that's the focus for various end markets. Oftentimes our products are mission critical. Everyone likes to say that, but in a nutshell, it's really the heart of some of the applications that we deliver into, especially in an increasingly electrified world. So to Fabio's earlier point, the permanent magnets are probably by mass not the biggest part of an EV, but they're quite critical because they are the heart that drive the electric machine. We call ourselves the undisputed technology leader in amorphous and nanocrystalline alloys, so I won't dwell too much on this because it's not part of the presentation today. And you know, we have a very long-standing and entrenched relationship with our customers. So in all, this led to a company history that's more than 100 years old. We have many patents to secure our technology. This is extremely important for us since we operate in a very competitive market environment. And we are proud to say that for many of our customers, we have relationships that last more than 10 years. So very close relationship. What are we actually doing? So again, I wanted to also mention the materials and components, soft magnets for sensor applications and common mode chokes, many things that also go into an electric vehicle. But we are the only scaled provider of rare earth permanent magnets. So that's where I want to switch the focus to outside of Asia. I will show a little bit of our footprint later, but we do cater to high growth markets such as electric vehicle motors and wind turbines. So again, as mentioned before, very light on the products, but I do want to show a very nice picture of our world that displays the multitude of applications that consume permanent magnets. We deliver into buildings, elevators. Bread and butter business is robots, servo motors for Industry 4.0, molecular pumps. We also produce magnets for very funky stuff like scientific particle accelerators. And of course, EV traction motors. I will give an example later. And also wind, a topic that is very much in everybody's mind, given the energy transition. So again, what are the past 40 years? And I think it's good to show that in terms of a global footprint where our products are produced. You can see that as WAG, we are a European focused centric company that ventured out into Asia. And that's corroborated by our headquarter here in Hanau, where we have all the central R&D functions, you know, EMANS, we have regular exchanges. I love your slides about rare earth saving technologies, grain boundary diffusion, that all happens here. We do have in green all the plants that are dealing with permanent magnet production, which is in Slovakia. We have a complete factory integrated in Finland. We also have a joint venture in China, so very good relationships with this country. And then two more plants for the soft magnetic materials. And what we are currently doing, leaving our 40-year history of permanent magnets in Europe and Asia a little bit behind, is we are expanding in the US, in Sumter, South Carolina. This is a plant that will be exclusively dedicated to the production of permanent magnets for electric vehicles. And I can give a little more details on the next slide. And it leads a little bit into the question of where do we want to go and how do we get there? Because as WAG, again, the only scaled provider for rare earth permanent magnets in the West, we see it as our, let's say, duty and opportunity to support the trend and growth of these energy or let's say carbon neutral technologies such as EV and wind turbines. And with this first factory, we were able to demonstrate that we are serious about that. So here's a quick snapshot of the US plant with a headline: US leads the way in securing Western critical mineral supply chain. It's a little bit provocative in the context of the European EIT Raw Materials Society and the Magellan project, but I think we need this reality check of how are we doing on our trajectory. And this is not exclusively for Bach wants to do everything, but we are in this all together. This supply chain, believe me, is complex enough. So there's a lot of opportunity for a lot of players. But coming back to this example for General Motors, we were able to secure a contract for the supply of permanent magnets, and we are currently building the factory. The interesting thing is that we had a very strong push from the US government towards a resilient supply chain. Everybody knows Inflation Reduction Act, which is a huge driver for a lot of investments that take place there. There are other vehicles from the Department of Energy and Department of Defense that want to strengthen this supply chain. And that's all, sidelined, if that's the correct word, by quick permitting processes and a strong support by political parties and local community. And basically, this is in my opinion, it's a very strong recipe for building up with a good speed of execution a resilient supply chain. I mean, we've started building this factory beginning of this year, and this is a snapshot of I don't know, a couple of weeks ago. So it's a very quick timeline of execution. And I hope that this is not only one example, but that there will be many more examples, probably, hopefully, or we wouldn't be against a spearheading part in this whole venture. But again, the market is big enough, so we need to collaborate to make this happen. So let me end up with a European perspective. In my opinion, the European actors, they need more speed and certainty to reach the 2030 goals, because 2030 is right around the corner. And I think we have two political frameworks that are excellent regulations. First, the Critical Raw Materials Act. I'm sure everybody in this auditorium knows about the details. It is good to have the benchmarks for rare earth processing. There are, of course, other important critical minerals, but in particular the rare earths. And also the Net Zero Industry Act. Again, this is a little bit further downstream, so not the processing part, but more which applications, such as offshore wind, heat pumps, batteries, and storage. And the critical minerals or the critical components, I have to say, for such applications, they need to be included here in this net zero industry technology. And I hope that we can make these acts more robust in the execution and provide the necessary guidelines for industry to really have security of planning and also to have a strong support for the business risks that companies will have to take if they want to invest in this. So my four main messages are that as SWAG, we are proud to be the only scaled provider outside Asia. We have the technology at hand, a lot of experience in manufacturing these magnets. They play a mission critical role in Europe's targets for resilience and carbon neutrality. I do believe that the two acts are exactly the right tools to guide market participants towards a competitive, resilient, and sustainable supply chain. But we need more details regarding permanent magnet production and usage to avoid unintended loopholes. And then, of course, the recurring topic is how do we get access to the capital and the speed of execution? And this seems to be lagging a little bit behind in Europe compared to the US. So that would be my summary.
Thanks very much, Alex. Very impressive to see the expansion in the US. It must be an exciting moment to really ramp up a new production facility with the latest technology. So we have time for questions. So let's have a look at the Q&A window. Vanessa or Alex?
Yeah. We've got Nabil, who's asked, we're all discussing about building Western mine to magnet supply chain, but somehow all companies entangled with Chinese actors. You still have a strategic relation with Sanhuan, a Chinese company. Are you still depending on them for the technology and materials?
Excellent question. Yes, and maybe to make this statement very, very clear, I think people who know me have heard this a couple of times. This strategy is not against a single country, be it China, be it Germany, be it France. This strategy is more towards a diversification of supply chains to move it away from a single choke point. Yes, we have very good relationships to many Chinese suppliers, and especially our dear JV partners in China. But in addition to that, and not because of that, we do want to also have an outside of China supply chain for a topic that some people call local to local market, or for a simple diversification of supply chains. I mean, it's business 101. Don't be dependent on a single supplier. The OEMs know that very well, but we seem to forget that at some point in time, and then try to, maybe construct or whatever, have this argument that is contra somebody or pro something else.
It's about de-risking the entire value chain, right? So it's that de-risking and diversification.
Yeah. And maybe if I may add to this point, this also brought us in a position where we already today have a supply chain that's vastly independent from Chinese sources. It's a very small stream, to be frank, because it is not scaled at the moment. But from what I see in the upstream business, basically mining to, let's say, alloy, there are a lot of feasible players. So I'm less concerned about do we have enough, but more concerned about how do we get the rubber on the road, right? How do we get it executed?
That would actually that would be my question to you. I mean, you presented it very nicely and very concise. I mean, what would be the next key step to kind of mirror that success case with GM, with a big automotive supplier, or energy technology provider in Europe? So what would be the next key step?
Yeah, so I think there are two main components. One is the OEM commitment to this supply chain. It's the most important one, and this has been activity spearheaded by General Motors in the US, not only for permanent magnets, but for a couple of other critical components. And this is critical, like for all the other upstream suppliers, because it gives a certain amount of security in the business planning. And I also understand that there's a risk for the OEMs. So in order to make them comfortable with the commitment, we need this first decision point, which is commitment by the OEMs, supported by a strong regulatory framework that is very clear. Because if we start diving into CRMA and NCAA, we find that it's pretty good, but there's still a couple of open questions towards the end of, what happens. Just to give an example, if in the Critical Raw Materials Act, a market participant does not have 25% recycled material, or does not have critical raw materials that's processed to 40% in the European Union. At the moment, maybe nothing. So
I mean, we will have the outstanding opportunity then to ask these questions and reflect with one of the key players at the European Commission behind the CRMA later on. It's Milan Grochul will later on, after the next talk, will give his insights here. Thanks very much, Alex. Very exciting. And now I would like to move and give the words to Benoit Richepet, who's actually talking on behalf of Orano, and a company with a long history in uranium processing, energy technologies, and so on and so forth, now moving into the rare earth sector. how on earth do you make this decision in this competitive landscape? Very happy and to have you here to tell us about your activities.
Hello, everyone. So thank you very much, Roland, for this introduction. And Alex, not very easy to talk just after you, but we're gonna try to explain you why do we feel that at Orano we can bring something quite substantial for the recycling of permanent magnet while still reaching high performance, because this is really what we do believe in. So first of all, Orano is a nuclear company. We are owned at 90% by the French state. And what we do is that we operate in the nuclear fuel cycle, from mining, transformation of the uranium, and then we recycle the used nuclear fuel with some techniques that can be leveraged for the permanent magnet recycling. We also have processes that can be leveraged to invent tomorrow's business, such as alternative treatment for targeted alpha therapies, the recycling of battery material, etc. And we have opened 2 years ago the recycling and manufacturing of rare earth permanent magnet. So actually, we do have a considerable know-how that can be leveraged in this field. With the core activities that I introduced you with, we actually have strong know-how in hydrometallurgy, pyrometallurgy, powder metallurgy processes in the nuclear fuels that can be translated to permanent magnet recycling. We are also experts in processes industrialization, and interesting as well in the industrial production of complex powder, plutonium powder in inert atmosphere. And on the right part of the slide, I just put a snapshot of our MOX fuel production in the south of France, where we do make this recycling of used nuclear fuel. And funny enough, but 75% of the process is actually what you need to master to manufacture and recycle permanent magnet. So we have the techniques, some of the techniques, we have a recycling know-how, and that's the reason why we entered into this diversification program 2 years ago. We don't have actually all the technical competencies. We are perfectly aware of that. So we teamed up with the CEA Liten from Grenoble, who has been accumulating since 10-15 years a lot of expertise in magnetic material. And we are developing with them patents for short loop recycling with hydrogen decrypitation or short loop recycling by melting. The rest of the techniques have been introduced by Iman, so I'm not gonna dive into too many technical points. But what you need to remember is that we are really focusing on short loop recycling, and we want to achieve high performance. We don't want to do downcycling, you know. We at Orano, we really target high quality. So looking at the rare earth and permanent magnet value chain, you can really see that on this value chain, we are developing processes for the short loop powder, the short loop alloy, with 2 projects, Magnolia, supported by the French state, and Magellan, supported by Horizon Europe. And that's the reason why we are here today with our colleagues in order to scale up this short loop processes. And our end game is in 2 years, we are able to scale up these processes in order to produce high performance sintered neodymium iron boron magnet, reaching EVTM and wind turbine grades with at least 25% of secondary raw material coming from the short loop. So why the short loop? Because I told you we have this technical capabilities, but also because for 25% of the material, which is already quite good, we will avoid the strategic segment of metal conversion that is not at all developed in the Western world. So this is really the value proposition we are focusing on, and we will be starting in a few months, actually, a pilot plant in Grenoble in order to scale up this process. So we have Magnolia, as I told you, with all our R&D activities are taking place in CEA Litten in Grenoble. Magellan that I'm going to detail in a few slides with a lot of very valuable partner. And we are preparing our third step with this pilot plant in order to achieve really the high grade and to enter into the qualification campaigns with end users, both from EVTM and from offshore wind sector, so that we really demonstrate that not only we can manufacture lots with high performance and 25% recycled material, but also that we can demonstrate repeatability and reproducibility study. So this is really our next step and what we are focusing on at the moment. So looking at Magellan, I must explain a bit what is a Magellan consortium, that you have here a snapshot of who is involved, and we have here CRF, we have heard the IT, but there is a lot of people involved. And in short, some of the most important KPIs is that in Magellan, we develop a magnet to alloy route in order to achieve a yield above 70%. We are also developing a near net shape magnet in order to achieve more than 50% reduction of the material loss. We want to increase the EVTM recyclability so that the used magnet can be easily extracted once they are used. We want to achieve a TRL 7, as I told you, in 2 years' time. And we want, of course, to make sure that this process has a significant positive impact by reducing by at least 50% the carbon footprint. So that's all my short presentation. And if I can try just to sum up, so we have a lot of technical know-how coming from the nuclear fuel cycle, and we want to extend them to the permanent magnet recycling. Second is that we want to achieve high performance magnet with 25% recycling coming from the short loop, and that is super important for us in order to work both on circularity and resilience. And we are starting our pilot plant in a few months. Thanks a lot.
Thank you very much, Benoit. So it's like a role model, right, of an industry player in Europe, transitioning from one sector to another in close collaboration with research organizations. And in particular, here you mentioned CEA. That's very impressive. Now I'm looking at Vanessa.
Yes, we have a question.
Yeah.
What are your end-of-life streams for recycling? Will you collect enough materials?
So today, it's true that collecting used magnets is not easy in Europe. Today, for the 2 and 3 years to come, this is not a big issue, because what we need to do is to demonstrate that our process is really working. So we are looking for hundreds of used magnets, which is not that complicated to find. And then once the process will have been industrialized, I really believe that it will be key to partner with the end users who will actually have their hand on the used magnet. And I think this is achievable both from EVTM sector and offshore wind. But another way to answer your question is that we are not really interested in cheap magnets, because if we have a cheap magnet in entry, we cannot remanufacture a high performance magnet. So we are really focusing on the future used magnet from EVTM and for offshore winds, which means the business model is actually simpler to put in place with the big players.
Mm-hmm. I have another question. Have we got time, Roland?
Yeah, go ahead. Go ahead, Vanessa.
What is the current state of the Magnolia and Magellan projects?
So today we have achieved our first period of R&D. So we are able to manufacture relatively good magnet, and we have started to introduce a certain percentage of used magnet in order to remanufacture new permanent magnet. And we are busy actually installing the pilot process plant at CEA Lytton in Grenoble, which will soon be operational in January next year. And then we will be able to start the second phase of R&D, trying to introduce more capacity and achieve higher performance in our prototype.
Thank you very much. Thank you very much for your presentation and the discussion. We'll have a bit more time at the end after our last speaker now. That is Milan Grohol of the European Commission. So I'm really happy to have you here, Milan. And you've heard to all these exciting presentations, these initiatives from research side, industry side. And I know that you've been following this topic for a long time. So I'd love to hear your view on really how the European perspective, and then of course the European Commission's perspective. So I will share your slides. I hope this works out. Let me check, and then word over to you. So let's see.
Thank you, Roland. Thank you very much for a kind invitation. I don't know if you hear me and see me because I had some technical issues to join.
Yeah, we can hear you well.
It's a problem on our side. I'm sorry for that.
And you see the slides, Milan? And
yes, I'm fine. Perfect.
Okay.
So my name is Milan Grohol. I'm from the raw materials unit of DG GROW, which is an equivalent of Ministry of Industry at the EU level. I would like to go through a few important developments in the Critical Raw Materials Act and focus especially on magnets. So, Roland, if we can go to next slide, please. So here, only one important information which I want to mention is the Act entered into force on 23rd of May 24. You will see it is a regulation actually, and it is applicable as it is in all EU member states. So this is very important. So it's not a directive which has to be somehow transposed. This is something which works as it is in the whole EU. That's one thing. And second, the whole regulation is relevant for strategic raw materials, and I will show the later rare earths and other materials are strategic. That means that all provisions of the Act are relevant to the rare earths and magnets, related magnets. Next slide, please. Okay, so I will do short overview. What is important in this Critical Raw Materials Act, in the regulation? Let's start with the monitoring on the left side at the top. It's monitoring and building the intelligence in the EU. We will perform again every 3 years criticality assessments, revising the list of critical and strategic raw materials. We will start the assessment again next year to be published towards the end of 2026. We will work on methodology on stress testing for strategic raw materials. This includes also the rare earths. And of course, we continue with foresight work and bottlenecks analysis with colleagues from Joint Research Center. And we are also collecting information on production projects across the whole EU. So that's something which we do with member states, but we also have the information coming from strategic projects. I will come to that a bit later. We are also on the risk mitigation side. We start implementing the provisions on joint purchasing platform. The tender is launched with colleagues from DG Energy related to demand aggregation for natural gas, hydrogen, and strategic raw materials. We have not chosen yet the pilot strategic raw materials which will be there. It's an IT platform. It will start in the first half of next year. Strategic stockpiling is another topic which we launched, which we will start discussing with member states. First is the the information collection, and then coordination of strategic stocks in different formats. Also, probably collaboration with industry would be needed. Regarding strategic projects, I will come later. I have a slide on that. We are developing strategic partnerships across the world. We have signed already 14. On exploration, we push member states to develop their exploration programs to find new deposits and finance that. If possible, we will see what can we do also to support at the EU level later stage when we see the programs. We also ask member states to develop the circularity national programs to promote reuse, collection, recycling, so everything what we heard today. And there are also provisions on the magnets, which I will mention later. We will have also provisions on certification schemes and environmental footprint, but I will skip that for now. What is very important is that for the first time, we have benchmarks which give European ambition to secure domestic supply to cover our needs by extraction at least by 10%, processing capacity at least 40%, and recycling 25%. So this is for some materials it looks very high, for some very low, but these are in reality very, very ambitious benchmarks. There is one benchmark which is the diversification of supply, and that's I would follow up on Alex's point that what is important is to get away from the chokeholds of single third country. So that's very important. That's why we would like to reduce our dependencies on that. I will come to that a little bit later. Next slide, please. So very shortly, the Act targets, the whole Act or the regulation targets strategic raw materials which are green, and the rest are also critical. They are critical. The blue ones are only critical. The green ones are strategy and critical. So that's where you will see in the provisions, you will see the references to that. Next slide, please. There is maybe too much information for the moment, but I would, of course, the slides will be available after this roundtable. So here we have this slide showing actually where we have very high dependencies on single countries, and you see it's not only China. There are different countries on different materials, but for rare earths, it's definitely China, and that's the message. And here we are not talking about dependency of 60% or something like that. We are close to 100%, especially for heavy rare earths. So we understand also the efforts of industry to reduce the use. At the same time, we need to make sure that there is enough business case and in a big enough market to actually develop production of heavy rare earths. Next slide, please. Strategic projects. One of the major actions of the regulation was to launch the call for strategic project, which would benefit from three things. One, fast permitting, 15 months for recycling and processing projects, and 27 months for mining projects, which is unseen in the EU landscape for metal-related projects. So this is really very, very fast. Second, we will help with the help of the Critical Raw Materials Board of member states to help with to access finance, and we will also try to help connect with the off-takers. The first call and the first cutoff date on 22nd August exceeded our expectations incredibly. So we are counting 30-50 projects maximum. Here we talk about 170 applications in 42 countries. Only 70 member states, I must highlight. But what is very important, we have very good distribution of the projects across strategic raw materials and We have also 25 projects on rare earths and magnets. I'm very sorry that I cannot share more details. So, but it's very interesting to see detailed information on, and very important for us to see the potential in the EU. We just started the evaluation of the projects, and we will have to do it in 2 batches. So please bear with us. Our team can do it only as our capacities allow. This is the first of its kind exercise in the Commission. So this is not horizon evaluation, it's something else. It's assessment on financial side, technical side, environmental and social impact side, and also, of course, also the classification, correct classification of the projects. Next slide, please. I would like to go to another block of the critical raw materials regulation, and you mentioned the benchmark for recycling, 25%. It has been mentioned several times also by Benoit. We are nowhere with rare earths at the moment. In the EU, we are close to 0%. So to get to 25% will be really, really extremely demanding. And there we have to fix several things. One of the first things, and I would like to go to the next slide, please, is to understand what kind of magnets are on the market. So that's why we push for labeling of the permanent magnets. And we cover different types of magnets, neodymium magnets, samarium cobalt magnets, alnico ferrites. And we will have to do the implementing act to define the format of labeling by November 25. So it looks like far away, but actually we first need to do the study before, and we hope very much on the support of course of industry. I will mention that later in relation with the standardization. Then we will also like to have more information on the market operators, the weight, location, chemical composition, and so on. One thing which we want to make sure is that we will not put more burden on the industry, because there are several initiatives in parallel, including the Eco-Design for Sustainable Products and digital passport, product passport. So that's something where we would like to harmonize as much as possible. There are also developments in the end-of-life vehicles area, but we would like to do that. In our team, Maria Nyberg is the leader of this action, and we also team up with colleagues from Joint Research Center. So if you are interested from industry side to help, please let us know. Next slide, please. A little bit less urgent, but very important is also to promote the recycled content in the future. But the work will only start a little bit later. We have the first step. We have 3 years for developing the delegated act on calculation and verification rules for different raw material, for different materials. And then we may impose minimum requirements for recycled content only after 2030, unless there is a pressure from member states in the industry to do it earlier. So these are the 2 major labeling and the recycled content specifically for magnets. And I must insist that this is really a very strong magnets have been put in the focus of the Critical Raw Materials Act, also because of the previous work of battery colleagues, but then Roland and the team and the ERMA working group on rare earth permanent magnets, because that's something which placed it really at the forefront in front of the other technologies here. Next slide, please. So I mentioned standardization. We are aware of the rare earths ISO standard 298 committee, technical committee 298, hosted by China. We managed to motivate many member states to join actually this committee because several years ago when it started, EU was or the EU countries were mostly observing, and China practically copied their own standards. Last year, there was a new initiative to do a mirror committee, or the mirror committee has been set up at the European level, at the CEN level, and the secretariat is hosted by Germany. And in the latest discussions, it may evolve that the working group of this committee may help us with the labeling requirements of the act, the Article 28.2. So that's something which I would like to plea industry to get involved into the CEN TC 472, because that's something which may help also the Commission and them, and we want to help you to get the standards right and help the recyclers and users of magnets as well. And I would like to mention also another committee, if you are interested, and please help the International Standardization Organization Project Committee 348 on Sustainable Raw Materials. Again, the Secretariat is hosted by Germany. There we would like to cover the primary and secondary raw materials, different raw materials, and the whole value chain, and the sustainability is in the back, so that we don't get pushed out of the sustainability as our competitive advantage. Next slide, please. And that's one of the last slides. We finance a lot. We have financed in the EU from Horizon program. We have financed different strategic and critical raw materials, and definitely we spent a lot of money on rare earths and magnets, as this area has been very, very underfunded over decades. And these are not all projects, but these are the big projects which we do. We finance roughly 100 million euro per year in the area of raw materials from our team. And we are also waiting not only for the project like Magellan, but there are many more. There are some of them finished, and there will be 2 big projects coming as well. I would like to plea that the projects will also help us in implementing the Critical Raw Materials Act. And for that, I would go to the last slide. And it's the warm invitation to the Raw Materials Week 24. It will be 9 to 12 or 13 December. So main program is from 9 to 12. We will have on Thursday, we will have specific events or the sessions on building resilient permanent magnets value chain. We will have the session, so that will be in the morning. In the afternoon, we will have a session on circularity of permanent magnets, so directly linked to the implementation of the Act. And we will have also the clustering session, small session, side session, with the Horizon project, but also EIT projects. Thank you, Roland, for sharing.
Thank you very much.
Thank you.
This is great. Let me see if I can stop sharing. You still see the screen, I think, right? So,
yes.
Yeah, we do.
Okay, let me see. Okay, thanks very much for this presentation, Milan. I think this gives a very good kind of context of all the activities that we've heard before. And yeah, I'd love to invite all speakers to switch on camera. We have a few minutes left for one or the other question from the audience. I don't know, Vanessa,
Yeah.
Could you come in?
Yeah, sure. We had a few questions for Milan in the last presentation he's just given. One of them is Article 28 of the CRMA anticipates the introduction of a complementary act by November 2026 regarding the format for the mandatory labeling for permanent magnets. Will current and upcoming EU projects dealing with permanent magnets influence the requirements set for the labeling of permanent magnets? And if yes, how?
Oh, very good. So that's exactly the thing which I mentioned. Actually, the date has been corrected by in the corrigendum to November 25. So it's 1 year earlier. That's one change. And second, yes, we are talking to colleagues from Joint Research Center of the Commission. And of course, as I mentioned, also the standardization committee 472 at the EU level, the CEN committee. And we are really welcoming any help from the EU projects in this area. You can contact me or my colleague who is leading that, Maria Nieber, the ones who know her.
Mm-hmm. Next question quickly is, it's a question saying, I didn't quite catch the practical consequences of the law project on critical resource recovered from waste sharing. What would imply the transparency and the minimal requirements?
I'm not
sure
I understand the question.
Is this directed to whom is this directed?
This is to Milan.
Probably to me, yes, but I need to decode the question first.
Okay, we'll skip that one and move to the next one. It would seem very difficult to find native primary HREE and LREE in Europe or in the EU or even in Europe. In time for our transition, it could be even more difficult due to mining lead time. So in the specific rare earth industry, recycling is more strategic than in lithium found in Portugal, France, or Serbia. Do you share this view?
So HREE, so heavy rare earth elements and light rare earth elements, right? Just rephrasing the question a bit. Yeah,
I get it. I get the question. So, no, I'm not sharing this view. First, we have quite good deposits of heavy and light rare earths. What is the problem is to get them off the ground, and especially the projects which suffer from different weaknesses, either technology or access to finance or permitting. And our act will target that, or is targeting that through strategic projects. And we receive several primary raw materials of the rarest projects also in the EU. So recycling is very important. This recycling is very important, but without primary supply, it would simply not work. Our strategy has been since 2008 to have diversified supply, not only internationally, but also from primary, from secondary, and resource efficiency. So we would like to use all possible sources. This is what makes the supply chain resilient.
Yeah. Vanessa, final question, maybe also maybe to the rest of the speakers.
Let's see. There's a let's try this one. What about the issue of scale? Wind turbines use large size PMs different from the ones used in the automotive sector. How is the challenge related to recycling PMs for wind turbines in general? And what is the suggestion to reduce critical dependencies from China? We did have...
Yeah, maybe this is a question to Alex, Alexander Barsta, because you do actually both. You look into the EV sector and you also look into wind, right?
Yeah, so I think it's a very good question, and I want to give a two-parted answer. First of all, they have very different requirements from the product perspective. So wind turbine magnets, they operate at lower temperatures, and EV magnets at higher. So they have different composition and obviously a very different shape. The wind turbine magnets are very huge. The second interesting topic is the life cycle of the applications. EVs, we can say it's 10 years. Nobody really knows when an EV will come back for recycling yet. So it could be longer. But what's most certain is that wind turbines, they will be out in the field for 20 or 30 years. So it will take quite some time until we get them back. Once they're back, super easy to recycle. You get 2 tons of magnets with a very sharply defined grade. So for all the recycling companies where we are not active, this is a fantastic urban mine.
Yeah. And this is actually a good key word that leads us to looking ahead beyond this particular session of this Rare Earth Roundtable. So first of all, thank you very much to all experts that participated and gave your input. This has been really exciting. I think we have all the chain, all the key people, all the key sectors here. We have policy, we have research, we have industry along the value chain. So this is really the key to unlock, I think, a kind of a rare earth growth in Europe. And you just mentioned the urban mine recycling. As we indicated before, Magellan is a key item is recycling. So the next issue, or the next webinar that we will have on November 7th, we'll actually look into the urban mine. How can we extract material most efficiently from that urban mine, from this recycling potential that we have? So we'll share details in the next few days. Remember also the Raw Materials Week coming up that Milan Grochol just mentioned, with a dedicated day on rare earths, and not only kind of a session, but also kind of a clustering opportunity to meet the different projects and activities. And last but not least, I want to mention that at EIT Raw Materials, we invest into technology development startups in critical raw materials. But I can tell you, we have a particular appetite for rare earth, for the rare earth sector. So please check out our website, reach out to me personally, or to our colleagues in the different parts of Europe. We are really looking forward to get the good ideas, the good projects to really move ahead. So with this, thank you very much. Again, thanks to all the speakers, but also to you joining and listening and joining this webinar. Thank you very much, and goodbye.